Hi, welcome back to Kiersti's virtual classroom. Today we are talking about minerals. So these are the building blocks of rocks. Before we can start talking about rocks in this class, we need to learn a little bit about minerals. So let's get into it. All right, first things first, what is a mineral? A mineral is different than a rock. It is naturally occurring, inorganic, it's a crystalline solid with a definite chemical composition. It has to meet all of these criteria in order to be considered a mineral. So one question I would pose to you is naturally occurring ice a mineral? Yes or no? What do you think? It is because it's naturally occurring, so this would be like glacial ice. It's inorganic, it's a solid, it has a crystalline structure, and a definite chemical composition, which is H2O, right? So let's talk about different minerals and how they're formed. Okay, so how are minerals made? They are made up of elements, okay? So elements make up the mineral, and elements are made up of atoms. So remember, atoms are made up of subatomic particles, which are protons, neutrons, and electrons. Protons being positively charged, neutrons having no charge, and electrons being negatively charged. So as long as you remember some of those things, you'll be good to go. So this is a little bit of chemistry backup to kind of get us into minerals, because minerals are very chemistry heavy. So for instance, this diagram here shows you sodium and chlorine ions bonding together to make something we call halite, which is really just salt. So sodium and chlorine make salt, NaCl, and that's what forms halite. So the Earth's crust is made up of all of these different elements. Most prominently, our Earth's crust is made up of silica and oxygen. Remember, things like the inner core and the outer core, mostly iron and nickel. The crust is mostly silica and oxygen, along with a plethora of other elements. A lot of the elements that you see on the periodic table do not make a very high percentage of our Earth's crust, so they're a little bit more rare. They're harder to find, whereas the ones listed here make up a more significant portion of Earth's crust. What elements come from? A lot of them come from China, which is why a lot of our stuff comes from China, is because they have a lot of these elements and henceforth minerals in a very diverse form. So a lot of the imports of different things come from China, in addition to trade agreements and other political factors. But a lot of the elements are very widely found in China because they have a vast geology. Their geology is so diverse that they do have a lot of different elements, henceforth a lot of different minerals and a lot of different rocks that we could use. All right, so looking into the atomic structure of an atom, so you've probably seen this a little bit in chemistry, maybe even in physics, if you took that in high school or previously at Fresno City. So within a atomic structure, we will have a nucleus, which is where our protons and neutrons live. So that's where we have our no charge and our positively charged ions. And then we have electrons that circulate around that nucleus. And depending on what the electrons look like, they will bond with other elements that will satisfy the outer electrons. So if you kind of remember from chemistry, you need 8 outer electrons in order to be kind of stable. And if they don't, they look for something that will satisfy that 8 outer electrons around the nuclei. So in that case, they form bonds with other elements. So one of those bonds is an ionic bond. So in an ionic bond, this is when an extra electron on an outer shell is given away to satisfy the 8 outer shell requirement. So this is a type of bond where an element is bonded by one of the atoms giving away an electron to satisfy the other atom's outer electron shell to become stable. Okay. So this is a very typical type of bond. The next ones I'm going to talk about are a little bit more specific. So covalent is a different type of bond where they share 2 electrons. So instead of giving one away and then being left with 6 electrons on one atom, they share 2 of them. And by sharing them, they are bonded much stronger. So covalent bonds are the strongest chemical bond that exists in nature. This happens a lot with carbon. So carbon will bond in this fashion to other carbons. And this will form something like a diamond. So diamonds are made up of a bunch of different covalent bonds that are bonding together carbon atoms. And so you get a very strong little mineral there. Technically, diamond is a mineral. This is the closest to a diamond I will ever show you. And it is a very, very strong mineral. It is the strongest on the hardness scale that we'll talk about later, and it's because of these covalent bonds where they're sharing electrons on the outer shell. So getting into mineral groups, minerals are grouped based on the elements they're comprised of. So our two basic groups are the silicates and the non-silicates. The silicates contain silica and oxygen. Surprise, surprise, that's why they're called silicates. And those are the most abundant on Earth. So these are going to be the big guys. The olivines, the pyroxenes, the amphiboles, the micas, feldspars, quartz. We'll talk about all those more in depth. Those are some of the very major minerals that make up rocks that we'll look at in lab. And then the non-silicates do not contain oxygen and silicon. And then we have subdivided them into things like carbonates, halides, oxides, sulfides, sulfates, and native elements, which I'll show you all of those kind of broken down. All right, so within the silicate minerals, we have our major heavy hitters that we'll look at: olivine, augite, hornblende, biotite, muscovite. Biotite and muscovite are part of the micas. So if you ever hear me refer to the micas, that's the group that encompasses both of those minerals. The feldspars, quartz, and these are all divided based on their silicate structure and what else they are made of. So as you move down in this little chart here, you notice that the silicate structure gets much more complicated. And within the feldspars and the quartz, they have a three-dimensional network instead of just a two-dimensional network. And that yields a much more complex mineral. I'm not going to require you to necessarily memorize all of their chemical formulas and looking at their structures, but we will work with them a little bit. Okay, so quartz ends up being one of the most complicated silicate structures of the silicate minerals. All right, and then we get into the non-silicate minerals. So we have things like carbonates, which are made up of calcium carbonate. And then we have halides, which are made up of chlorine, fluorine, and bromide. We have oxides, which are made of oxygen, sulfides, which are made of sulfur, sulfates, which are made of silica and oxygen. And then we have native elements, which are single elemental minerals. So diamond is a single element mineral. It's only made of carbon. Okay. Things like gold, copper, sulfur, graphite, silver, platinum. Okay. So the carbonates would look something like this. You'll see calcite for sure in one of your labs. Dolomite is very similar to calcite. It's not as rock forming, so we'll show you mostly the rock forming minerals because there are hundreds of minerals out there. So the carbonates contain a lot of carbon. The halides, contain chlorine, fluorine, and bromide. And fluorite and halite are two that you look at multiple times. And these are some pictures of what they would look like. The oxides contain oxygen, so that would be hematite and magnetite. Magnetite is really interesting because it is magnetic. Hematite is interesting because it comes in this kind of specular form that you see here where it's sparkly. And then it can also come in the non-specular form, which makes it kind of like a rusty red. Sulfides are made up of sulfur, so here we have galena and pyrite. Pyrite is fool's gold. A lot of people mistake it for gold, but it has a much different density than gold does. It's much lighter. And then our sulfates are made up of silicon and oxygen. We have gypsum here. Gypsum is really easily scratched, as you can tell from the image that you see. We'll talk more about its physical properties later. And then we have our native single elements, which would be like silver, gold, sulfur, diamond, graphite. All of these they only contain one element. All right, so getting into the physical properties of minerals, this is kind of the bread and butter of this. This is where we can actually come to identify the different crystals. and try to tell them apart from other minerals. So the most diagnostic properties would be color, luster, streak, crystal form, cleavage, fracture, hardness, specific gravity. I'll go over each of those individually for you. And then we have other things that a mineral might have, which would be magnetism, it might have fluorescence, it might have a particular smell, like sulfur kind of stinks, and it might taste a particular way, feel a particular way, have striations, show double refraction, or it might react with acid. Okay, so we'll go through these individually. Color is usually the first thing that people notice about a mineral. And color is kind of deceiving because all of the minerals can come in a variety of colors. Some minerals only come in one particular color, but others will come in a plethora of colors. So quartz and fluorite both come in very similar colors, and they are clear and translucent, so they're really hard to distinguish if you're just trying to use color. So color is our least useful mineral property, although it's usually the first thing that people notice about a mineral. So here's an example of a bunch of different colors of quartz, fluorite, and beryl. So this is quartz here, this is fluorite, and this is beryl. If I handed you a bunch of different purple ones, but maybe one was quartz, one was fluorite, and one was beryl, you might not tell the difference. You might think they're all the same mineral, just because they're all purple. But it doesn't mean that they are. So be very wary about using color to distinguish between different minerals. It can be helpful, but just know that you can't always use it to distinguish. All right, and then we move on to luster, which is one of the more really definitive ways to tell the difference. Oh, we got a little typo here. So luster is the way that light reacts or interferes with the surface of the crystal. So when you take a crystal and you rotate it in light, what is happening to that light? How is it bouncing off of the crystal? So the basics are metallic and non-metallic. Does it look like it's made of metal? Does it have a metallic luster? If it doesn't, then you move on to non-metallic. And in the non-metallic luster, you can have dull and earthy, which is why I tried to combine these, but I missed the and. So dull and earthy are, they look more like dirt or dried mud, and it doesn't really have a particular sheen to it. Most of us know what mud looks like, so if it looks like it's reflecting light the way that mud or dirt would reflect light, you would call it dull. And then pearly looks like a pearl. Resinous looks something like dried glue. Silky looks like silk. We won't have any submetallics, but know that it exists. This is when you have a poor metallic luster. It is submetallic and is considered non-metallic if it has a poor metallic luster. And then we have vitreous or glassy, which will look a lot like glass. So think of the way that glass will reflect light. That is what vitreous or glassy would be. And then waxy looks a lot like wax. Now, when you're doing this in lab, I will say that resinous and waxy are really hard to tell the difference between. So I usually allow those to be a little bit interchangeable. So resinous, waxy, it's okay. As long as you're getting that it's not dull, pearly, silky, or glassy, we're on the right track. All right, moving on to crystal form. This is how the mineral actually grows. So when a mineral grows in nature, it creates some particular form. It takes some shape, right? And there are a lot of different crystal forms. There's some examples that are common are listed here. And things like the quartz crystals that you see here would be like a prism. You might see cubes, you might see dodecahedrons, octahedrons, things like that. But in lab, what you would do is you'll recognize those shapes, and then you'll try to draw them a little bit. And the important thing here is that this is not the shape that the crystal will always have. As soon as the crystal breaks, it no longer preserves its crystal form. So crystal form is the way that it grows. Once it breaks, we call it something else, which we'll get into next. So here are some more crystal form varieties, some different names down here. Some of the less common, less rock-forming minerals are listed down here. We'll only look at about 3 or 4 with some particular crystal forms. Okay, so next is hardness. So hardness is a relative measure of how robust a mineral is. So this is the Mohs hardness scale, which is a scale from 1 to 10. 10 being the hardest mineral and 1 being the softest. So we have a couple of different things that we can use to distinguish whether it is harder or softer than something. So we use a fingernail, copper penny, wire nail, a glass plate, or maybe even a straight plate. Okay, so if it scratches any of those items, then you know that it's harder than that item. So I have a couple of videos for the lab on this, but for instance, if I took a mineral and tried to scratch my fingernail with it, and it scratches my fingernail, it's harder than my fingernail is. Okay, so this is a relative robustness of the mineral against other objects. So as you can see, diamond is the hardest mineral on the Mohs hardness scale, and that's from those covalent bonds. That makes it very, very strong, whereas talc is the lowest. So here's the Mohs hardness scale with some pictures, talc being upper left here and diamond being lower right. So we have talc, gypsum, calcite, fluorite, apatite, feldspar, quartz, topaz, corundum, and diamond. And this will be really important for mineral uses because we need to know something about their hardness to use them for different things, right? So we can't use, let's say, quartz to make baby powder because it's too hard. Even if you ground it up, it's still going to be too coarse on a baby's bottom. That's why we use talc, or talcum powder you've probably heard of. It's a main ingredient in baby powder. And that is very, very soft mineral that once you grind it up, it's a very fine powder, and when you put it on the skin, it feels really nice. All right, moving on to the way minerals break. So minerals can break in 2 fashions. They can either exhibit cleavage or they can fracture. Irregular breaking is fracture. We'll talk about that in a second, but the beast is the cleavage. So when a mineral has planes of weakness, they will break along those planes much easier than any other portion of the mineral. So for instance, this is a muscovite mineral, and it has weak bonds in this direction. So these red are the weak, and the strong bonds are in this horizontal direction. So the vertical is where they can actually split. So you can take a knife and kind of split it right along those weak bonds, or sometimes they're so fragile that you can pull apart with your fingers. And that is breaking along those planes of weakness. So cleavage is breaking of the mineral along planes of weakness. Okay, so let's look at some more examples. So that first one we looked at is muscovite. So in addition to recognizing that it has cleavage, we also want to recognize that it has 1, 2, 3, however many planes it does have. Because depending on the bond between the elements, it will have different amounts of cleavage. So the muscovite has 1 cleavage plane in that one direction where it's peeling up like pieces of paper. Whereas the feldspar in the next one has 2. So you see a flat plane here and a flat plane here. So if you took the room that you were in, for example, rooms usually have 6 sides, right? You have 4 walls and a ceiling and a floor. So that's 6 sides to your room. You would imagine that if they were parallel, so if you take 2 sides of the room, 2 walls that are parallel to each other, that is considered 1 plane because they are parallel. That is 1 plane of cleavage. And the other set would be another cleavage plane, so the other pair. So when you're looking for cleavage planes, you're looking for pairs of parallel flat sides on the mineral. And if you took your room, it's basically a cube, right? So it would have 6 sides. And if you're looking at parallel sets of parallel sides, you just divide by 2, right? Because there's only 2 parallel sides for each direction. So you have a ceiling and a floor, so that's 1 cleavage plane. And then you have walls that go in one direction, and then you have walls that go in another direction. So that would be 3, right? So 6 sides divided by 2 is 3. But not all minerals will have that many flat sides as it has actual sides. So on this feldspar here, this side that's facing you is very rigid and rugged, and it's not parallel to the side that's on the other side of the mineral that you can't see. So we only have 2 parallel sides here, 2 sets of parallel sides, so you end up with 2 cleavage planes. Whereas if you move down here to the halite, this one has a lot of flat parallel sides, basically every side. So this is more of a cube like the room. Okay. So in addition to trying to figure out whether it has 1 side, 2 sides, 3 sides, you also need to figure out what the interaction between the cleavage planes are. So here in the feldspar, it has a cleavage plane here and a cleavage plane here, and the interaction between those two is approximately 90 degrees. Whereas if we look at the hornblende, you have a flat side here for a cleavage plane and another one here for a cleavage plane, and that interaction is like more like 120 degrees. So it's not equal to 90. So depending on what mineral you're looking at, it will be important to not only recognize that it has cleavage, how many sides, but what its interaction might be, because that'll help distinguish which mineral you're looking at. Then we move down here to halite. It has the 3 cleavage planes, and they are all about 90 degrees. Calcite is 3 directions, so we have 3 different cleavage planes here, and they're not at 90. It looks like it's kind of slanted, right? So if you took a bar of soap, for example, is what I have here, and you tried to figure out how many cleavage planes it has, mind you, it hasn't been used yet, you can use your fingers to determine how many cleavage planes it has. So what you want to do is you want to pair up fingers around the crystal, or in this case, the soap. So here I have 1, so that's a set of parallel sides, yeah? And then I have 2 here, it's another set of parallel sides. And then I have 3, which is my last set of parallel sides. So remember we did 1, 2, and 3. Hopefully you can kind of see it. So 1, 2, and 3. Okay, so this bar of soap would have 3 planes of cleavage, and if you look at the interaction, it's approximately 90 degrees there, right? Okay, so that's what you would do with a mineral if you were able to touch them, but unfortunately you're going to have to do this all virtually. So that would be for something simple like a cube. And then we get into something a little more complicated like a fluorite. A fluorite actually has 4 different cleavage planes. If you count all of its parallel flat sides, you'll have 8. 8 divided by 2 is 4. So that'll make it a little bit easier for you. All right, moving on to fracture. Fracture is the random breaking pattern. So not all fracture is the same. We do see irregular and conchoidal, but this is where you don't have any particular rhyme or reason to the way it's breaking. It doesn't preserve any shape or anything like that. So on the left here, we have irregular fracture, and on the right, we have conchoidal. Conchoidal looks kind of like an onion-like breaking. It breaks kind of in these half circles, so you can see kind of these grooves in the mineral that have broken in this concentric half circle fashion. And then the irregular breaking is just the random breaking. Random pieces, no particular reason or fashion that they break. Streak is the next mineral property we'll look at. This is the mineral in powder form. So a lot of the minerals we'll do this with is with the metallic minerals. Because the non-metallics a lot of the times will just leave white or clear streaks, but you can't see that on the white porcelain plate. And this is used to distinguish what metallic mineral you are using or you were looking at. So it's just the color of the mineral in powder form on a streak plate. Specific gravity, so some minerals are particularly heavier than others. In a lab, you might actually weigh and measure the volume of the mineral to try to determine its specific gravity. But most of these are going to be your metallic minerals because your metallic minerals are made of metals, and so they are particularly heavier than the other minerals are. Magnetism is another mineral property that you might see. This will be found with magnetite. So magnetite is strongly magnetic, and you can really easily identify it by putting a magnet or a paperclip or something like that against it, and it will attract it. So magnetite is really easy to identify using its magnetic property. Fluorescence is another mineral property that is a little bit more unique. These are minerals that will glow under UV light. Normally, when the fair is running, you can go into the rock and mineral booth, and they have a display of a bunch of fluorescent minerals that you can go into the little room. Many of you have probably been in there before and not even realized what you were looking at, or that we would ever talk about it in the future. But these, I don't actually have any of these. These are very rare, and they're usually fairly expensive to obtain. So we don't have any display at campus, or I don't have any at home, but they do have some on display at the fair. So in the future, when the fair does open, you could take a look at them. Smell, taste, feel. So some of them will smell, like I said, sulfur smells really bad. That's this yellow one here in the middle. It's very potent sulfur smell. Some of them will feel a particular way, and I might mention that. It might feel like soap. It might feel powdery, things like that. And then some will taste a particular way. So halite is made of table salt, basically. It's where table salt comes from. And it will taste salty. So if you actually licked the mineral, it will be salty. Striations are something that will occur in feldspars a lot of the time. And this is when you see basically hairline grooves in the mineral. So these ones have very good striations where they're basically grooves in the mineral. It's not the surface. So you could run your finger over the mineral and you're not actually feeling grooves. They're in the internal structure of the mineral. And the cousin to feldspar would be the potassium feldspar. So this is plagioclase feldspar that has the striations. Potassium feldspar does not. It has little waves and grooves in it that are lines within the internal structure, but they're usually really wavy. So you're looking for these hairline fractures that are very parallel to each other. And that's what's a good indication that you're looking at plagioclase feldspar and not potassium feldspar. Double refraction is another mineral property that you might see. So this one is often found in calcite. So this is when the light hits the mineral and it refracts in two different directions. It may be more than two, it could be three, but a lot of times in calcite, for example, which is what it's showing, it forms into two different directions after it hits the mineral. So the light goes in two different directions, so it looks like there's two of whatever is below it. So you could take it over some words and it looks like there's two sentences or two different words that you're looking at. So this is double refraction. And then we have reaction to acid. So some minerals that are made up of calcium carbonate, which is a base, will react to acid. This also happens in calcite because calcite is primarily made of calcium carbonate. And calcium carbonate will react with hydrochloric acid, and I do have some videos that you'll see of me actually using the hydrochloric acid on the crystal. And then lastly, we get into the Bowen's reaction series. So the Bowen's reaction series tells us something about how crystals are crystallizing out of a magma. So when a magma is cooling, whether it's above ground or below ground, it will crystallize different minerals. And depending on the temperature of the magma or the lava at the time, it will show different crystals. So the highest temperature magma or lava will yield olivine. So olivine will end up being a very, very small crystal, and it crystallizes at a very high temperature. Whereas things like quartz, which I showed you was very complex in its silicate structure, will crystallize at a much lower temperature. So this can happen either below ground or above ground, and it usually yields much larger crystals than the olivine crystals. And then we have all of these other minerals that are kind of in between that. And so in quartz, we'll see a very granitic or felsic igneous rock. And with olivines, we'll see a more ultramafic or mafic igneous rock. And we'll talk more about that with igneous rocks, but this is kind of an introduction just to get you familiar with the Bowen's reaction series. This will come in a lot heavier with igneous rocks. Okay, so that's it for physical properties of minerals. So I will see you guys in the next video. Bye!